Namaste friends, welcome to my channel, and today we are going to discuss the slope and deflection of this simply supported beam. Simply supported beam. Okay, please forgive my spelling mistakes. Sometimes I make mistakes, but don't worry. I'll make sure the derivations goes right. Okay, so this is a simply supported beam, and the easiest way to solve this slope and deflection problem is by quadruple integration method. Okay, what is called as quadruple integration method. Integration method. Observe that this particular beam, suppose this is x is equal to 0 and over here x is equal to L is the length of this beam. Okay. Now what happens is that you can fix a coordinate y over here and you can fix coordinate x over here. So usually this becomes an origin of this particular beam. Now if you see this particular beam, you can see that if xy is a coordinate over here, the beam have a very constant loading over here, which is something which is w. Okay, so how we will use this very easy way to solve the deflection problem of this particular beam. I will derive the the deflection equation and the slope equations for you right away and right now. So let's see how we are going to do it. The first thing that we're going to do is that we're going to write E and I. E is the Young's modulus, I is the inertia, and Y 1, 2, 3, 4. So 4 times we are going to integrate over here, which is equal to, see the load, it is constant. Okay, so that's it, W. Now what we will do next is that we will integrate this equation. Integrating 4 times we get, so the first time if we integrate, what we will get is that E into I y triple dash is equal to W into x plus a. Okay, uh, and we'll get a constant. Then again integrating this equation, we will get W into x square by 2 plus ax plus b. Again integrating this equation, we will get y dash is equal to W into x cube by 6 plus a into x square by 2 plus bx plus c. Okay, again integrating this equation, what we end up is that E into I is equal to y is equal to W into x power 4 by 24 plus a into x cube by 6 plus b into x square by 2 plus c x plus d. Okay, see over here what we have got is, over here is that we got 4 a comma b comma c comma d as constants. Okay, now if you carefully observe this equation over here, since a b c d are the constants, now you carefully observe this equation over here. This particular beam has moment diagram something like this. You have a moment diagram something like this. It's a parabolic equation. So moment over here is 0 at x is equal to 0, and moment over here is also 0 at x is equal to L. Okay, and if you see the deflection curve of this beam, it will be something like this. Okay, so at x is equal to 0, delta is equal to 0. At x is equal to 0, delta is also x is equal to L. So as this beam is there, Okay, so this will be the curvature of the beam. Okay, xl and delta l. So we are going to use these two boundary conditions to solve a, b, c and d. Okay, let us use this first boundary condition over here. Now, as you can see that this is a quadruple integration method. So the first equation is loading. Okay, the second equation gives you the shear force. The third equation gives you moment, that is m. And the fourth equation gives you slope, that is theta. And the fifth equation gives you deflection, that is delta. Okay, now we have got this all this equation. Now see our boundary conditions. We have taken only moment and we have taken deflection. Okay, we have taken moment and we have taken deflection. So we have to take moment equation and the deflection equation out of these two. Okay, so this is the equation that we are going to take, and this is the equation that we are going to take. Okay, so let's take moment equation first. Okay, let's take the moment equation first. I will write the moment equation as it is. Okay, ei. Okay, it's not visible. Okay, right here. Okay, ei y double dash. See, I'm writing only this moment equation is equal to w into x square by 2 plus ax plus b, that is equation 3. Now this is the boundary conditions that we have seen, that we have seen. M is equal to 0 at x is equal to 0. M is equal to 0 comma at x is equal to L. We will use these two boundary conditions to find a and b values or expressions. Sometimes we get expressions for this. Okay, just follow me. As I have taken this equation, let's substitute 1 over here. Moment is equal to nothing but y double dash. Okay, so y double dash is equal to 0 at x is equal to 0. So this is 0 square by 2 plus a into 0 plus b. So something multiplied by 0 is 0, anything multiplied by 0 is 0. We get 0 is equal to b. Henceforth, b is equal to 0. So our constant b is equal to 0. Let's apply the second boundary condition over here. That is e into I into y double dash. See, moment, this is also equal to y double dash. Y double dash is also equal to moment. That is 0, which is also equated to x is equal to L. So w into L square by 2 plus a into L plus b. As we have seen that b is equal to 0, we can put b is equal to 0 over here. W L square by 2 plus AL, and taking out wl square by 2 on this side, we can write al is equal to minus w into l square by 2. This l and this 2 cancel. A is equal to minus w into l by 2. We got our second constant. See, in this method, by taking by taking the moment only, because for simply supported case, moment at the both ends are 0. Moment at the both ends are 0. So we have taken this boundary condition and easily we have solved a constant and second constant. The third constant is C and D. Now, using the deflection, uh, using the deflection curve, we know that for a simply supported beam, the deflections at the both ends are 0. So at x is equal to 0 and delta is equal to 0, at x is equal to L, delta is equal to 0. So we will use our deflection equation. This is the deflection equation which we have derived by using 4 times integration. 4 times integration we have derived this equation previously. Now I will use this equation and I will find the C and D values. So let's go ahead and let's find the C and D values. Okay, I will write down this equation as it is for you, and okay, I hope I am visible. E into Iy is equal to w x power 4 by 24 plus a into x cube by 6 plus b into x cube by 2 plus c into x plus d. So as we have seen in the previous case, 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 we have found that if value of a over here and the value of b is 0. So substituting these values first, value of a is equal to minus w into l by 2 plus, okay, and b is equal to 0. So what happens is that we get I into y is equal to w x power 4 by 24, okay, plus minus wl by 2 x cube by 6 plus b is 0, so 0 multiplied by x cube by 2 plus cx plus d. Now after some modification, this 0 into 0 is goes off. Wx power 4 by 24 minus wl by 12 into x cube plus cx plus d. So this is the equation that we are left out with. As I have discussed earlier, see these boundary conditions. Okay, at x is equal to 0, delta is equal to 0. At x is equal to 0, delta is equal to 0. At x is equal to 0, delta is equal to 0. At x is equal to L, delta is equal to L. Delta is nothing but y. Okay, so we'll write these conditions over here and let's go further. Y is equal to 0 at x is equal to 0, y is equal to 0 at x is equal to L. Substituting this boundary condition over here gives us 0 e into I into 0 and x is equal to 0. So w0 24 minus wl by 12 into 0 cube plus c into 0 plus t. So all this 0 into 0 0 0 into 0 is 0. So you end up d is equal 0 is equal to d comma d is equal to 0. So d becomes 0. Now applying the second boundary conditions, what we get is that applying the second boundary condition, y is equal to 0 at x is equal to L, e into I into 0 is equal to, let substitute L in this equation, wl power 4 by 24, okay, minus wl by 12 into L cube plus C into L plus D. Okay, as we know that D is equal to 0, we can put it over 0 over here, and we can write WL power 4 by 24 minus WL power 4 by 12 plus C into L. Okay, so till here we have to find what is C value. Taking L as a common, we can find that WL cube from by 24 minus WL cube by 12 plus C. See, this is 12 over here. What we can do is that we can multiply by 2. So 12 into 2 is 24, and we can multiply by 2 and divide it by 2. So what we get is that 0 is equal to WL cube by 24 minus 2 into WL cube by 24 plus C. Okay, I'll write it over here, and as you can see that 0 is equal to W into L cube by 24 minus 2 into L cube by 24 plus C. So 1 minus 2 is minus WL cube by 24 plus C. C is equal to WL cube by 24. This is our final C value. Okay, so hey, just look at it. We found A, comma B, comma C and D values. Okay, and we have seen that uh, D is equal to D is 0. Okay, let's go back to our deflection equation again and substitute these values, as this is our equation. Okay, so D is equal to 0 and C is equal to WL cube by 24, and previously we have solved for B is equal to 0 and A is equal to minus WL by 2. So how this turns out that E into I into Y is equal to WX power 4 by 24, and what is the value of A? The value of A is minus WL by 2. Okay, plus minus WL by 2 x cube by 6, and what is the value of the B? The value of the B, where is it? We have solved the value of the B over here as 0, so this is 0, so don't need to write about it. And the third thing what we have got is the value of C. So the value of C over here is WL cube by 24. Okay, plus WL cube by 24x plus what is the value of D? The value of D is 0, so no need to write this. So our final equation E into Y Wx power 4 by 24 WL by 12 into x cube plus WL cube by 24 is the equation, and finally we have reached it. We have done it. 1 by EI into Wx power 4 by 24 minus WL by 12 into x cube plus WL cube by 24. This is our this is our this is our final deflection equation for the simply supported beam. Okay, this is our final equation for the simply supported beam. This derivation is very common, and this derivation is also useful in many competitive examinations and also in the civil engineering also. this derivation becomes very important for the simply supported beam. For simply supported beam, what we have done is that we have used quadruple integration method. In the quadruple integration method, what we have found is that we have taken E into y double dash is equal to W. Now integrating 4 times, what we have got is equation 1 shear force, equation 2 bending moment equation, equation number for slope 4 for the slope, and equation number 5 for the deflection. So we have to find the constant a, b, c, and d, and in this particular constant, in this particular derivation of finding the constants, we have found that b and c are 0 and a and c are the values that we have derived, as a is equal to minus wl by 2, and the value for the c is something which we have derived previously as C as WL by 24. Now, after that, we have substituted A and C in the equation. We have finally derived at our master equation for the deflection equation of the beam. Okay, so this works uh, for the value 0 less than x less than L. Okay, if you have doubt like that, whether this is going to sorry, I'm sorry, they have to be c, you can check it also. At x is equal to 0, you have to get y is equal to 0, right? At x is equal to 0, y should be 0, right? Just put in this equation, this will become 0 0 0, so finally you will get delta is also 0, so this condition is satisfied. I will solve some problems related to it which will help you for further understanding in the upcoming sessions. So till then, this is asked in the university examination, and some short questions are asked on the simply supported beam in the very prestigious examinations like GATE, UPSC, civil services examination if they choose engineering as a branch, and this deflection equation, mostly they will ask for a long answer type questions like 10 marks questions or 20 marks questions. At that case we have to uh, derive this equation. Okay, so till then, take care and have a nice health. Bye.